Alright, trying out this problem, sort list. Given the head of a linked list, return the list after sorting it in ascending order. So this is the list, you sort it and you return the list, the sorted list, okay? Example 2, this, again sorted list. Basically, just sort the damn list, okay? Constraints, number of nodes in the list is between this, node values between this. Follow, we'll do the follow-up later, but let's have a read still. Can you sort the linked list as O of n log n time and O of one memory constant space? Mhm. So when it says constant space, does it mean we do it in without creating a new list or something? Okay, let's first think how we'll sort it. What would be a good way to sort a list without using extra space? When you say extra, without using extra space, maybe merge sort is out of picture. It requires extra space. Whatever algorithm that we need. The problem with a linked list as compared to an array is that in an array you can access any element in O of one time. While in a linked list to access an element of at index I, you need to traverse I times. So we want to reduce the number of traversals. Hmm. Okay, so n log n means we take either in like a merge sort or a quick sort. Merge sort usually for array might take extra space, but I think for linked lists, sort like merging two sorted linked lists is something that we have done that can be done in place. So could we try a merge sort here? That's the question. So what would it look like? So our linked list is 4, 2, 1, and 3. If we have to break it into two, firstly you'll have to find the middle. Finding the middle can be done in O of n. Uh, you traverse to that point and you then say, hey, sort 4, 2. So this breaks into sort 4, 2, sort. Okay, so let's call it. So we're sorting this list. This breaks into sort 4, 2, sort 1, 3, and then merge the two, which would then further break into sort 4, sort 2, merge, and sort 1, sort 3, merge, and finally these two lists. Okay, so these are being merged here. So yeah, I mean, makes sense. So you'll get your 2, 4 has to be sort of merged with 1, 3, and then when you do the merging, you'll get 1, 2, 3, 4. Hmm. Need to be a little bit wary because what is 3 is next pointing to, what is 4 is next pointing to in the original tree, in the original list, and you might have to break them. Yeah, fair enough. Let's still try this merge sort thing then. Okay, so first we need to find the mid. Okay, so how do you find mid? We can take a slow pointer and fast pointer thing. Because it's not, yeah, so we can take a slow pointer and fast pointer. So then I also need to ensure that first dot next is not null. Let's take a couple examples quickly for this mid. What happens in case of 1, 2, 3, in case of 1, 2, 3, 4, and in case of 1, and in case of an empty string. So quickly here, fast pointer and slow pointer both are here. Fast is equal to first dot next. So fast goes here and slow goes to 2. And then you can't move forward. So your mid is equal to slow. Now in case of 1, 2, 3, 4, fast is here, slow is here, fast goes to 3, making some mistakes. Okay, fast goes to 3, slow goes to 2, fast goes to null, slow goes to 3. Yeah, so 1 to 3 and 3 to null. Um, yeah, you could either take this or you could either take this. Either is fine. So yeah, so basically then your right one should just be considered as uh, yeah, this is a problem sort of. Uh, like in this case, I would basically have to break into two parts, right? So you can break from mid, right? Here I break from mid, fair enough. Instead of mid dot next, you'll break from mid, and that will be considered as a right. So you need mids previous as well. Um, Mids previous, huh? So we could do previous is null, and then you do slow equals to slow dot next. You could do before that you could do previous equals to slow. So looking at this, yeah, one will go to 3. Your slow would go to 2 and mark 1 as previous. 3 will go to null. 2 will go to 3 and mark 2 as previous. So this and this is what you get. Okay. Now you have to sort of break uh, from the middle. What does that mean? Hmm. So your previous was next you set as null. Okay. So in this case, it will become 1, 2 null. 1 we already have as head. 3 we have as mid. And 4 next is anyways null. So now we call this thing sort list on head. Then we call sort list of mid. And then we call merge lists where we pass in head and mid. Now does this continue to work is something that we have to figure out. I think so, right? So let's do this merge list. Call it merge sorted lists. Hold on. So we have to return head. Okay, so we can do this. Return merge sorted lists, and it's its responsibility to return some head node. What we do know is these lists are almost equal in size, so we don't really care which is bigger, which is smaller. One might be one bigger and smaller. Do we know their sizes? Potentially we do, but does it matter? Uh, well, from these experiments, we know that it's the right guy, right? So left and right we can do. So we can just call it list one, list two. So we know either they're equal or head two is larger always. That's how we are dividing. Mhm. Okay. So basically, let's do this. Let's do that. Hey, we'll always consider head one as the list, right? So first thing is if head one is null, you return head two. If head two is null, you just return head one, right? That is fine. Now we ensure that we're always which one is smaller actually. Whichever is smaller, that's the guy we choose. Fair enough. Whichever is smaller, that's the guy we choose. So if isn't it head one is the guy, so let's do this. So if head one dot val is less than, then it's fine. But if head one dot val is greater than head two dot val, is it called val or yeah? So if then we wanna uh, do a swap. We want to ensure that head one is smaller. Are we swapping the values or are we swapping the nodes? Hmm. We're swapping just the variables, head one, head two, right? Yeah, that's all. That's the only thing that we're swapping. Yeah. So whichever list is the first guy is a smaller one that we'll consider as head one. So we could very well just do basically return merge sorted lists of head two comma head one, right? That is also sort of swapping. Now when we come here, we know that head one is smaller or equals, which is fine. So now so we can just return head one without any problems, right? That's the point. And now we do list node one equals to head one. List node two equals to head two. And while node 1 is not equals to null, and then node 2 is not equals to null. Okay, so now we know that the node 1 is the smaller guy, that we know for sure. So we have to compare two things. One we have to compare is node 2, another we have to compare is node 1 dot next. Okay, so there are two cases. Firstly, if yeah, this null is another problem that we have to handle. Because if node 1, yeah, node 1 can't be null, that's clear. And if node 2 is, to begin with, neither of them will be null. That makes sense because we have checked those here. So begin with, none of that will be null. So now we have to consider node 2 is not null and node 1 not next. So node 1 dot next could be null. So if node 1 dot next is either null, or that means we can't go to node 1 dot next, we have to go to node 2 only. So other case then we have to go to node 2 is if node 2 dot val is less than uh, node 1 dot next dot val, right? In both these cases, node 1's next in both these cases node 1's next has to be made node 2. And then what happens to node 1 next, actual node 1 next, that has to be called node 2 now. So you swap node 1 next as node 2. Okay, so yeah, so node 1 dot next is node 2, and node 2 is now node 1 dot next. So now again, and basically we have to also do node 1 to node 1 dot next. Okay, that is anyways has to be done, right, after changing the next. So else case is what? Else case is in the other case, node 1, the next guy has to be node 1 dot next only, and yeah, so that is fine. So only thing that needs to do is node 1 equals to node 1 dot next. Now what happens if node 1 dot next is null, is indeed null? Well, node 1 dot next cannot be null, right? If node 1 next, I mean, if null, then you can break, obviously, because we would have pointed, yeah, we would have pointed, if node 1 dot next was null, then would have actually pointed it to node 2, and if node 2 is also null, then fine. So that's the last condition. So okay, all good, we return head 1. So this is the merging, this is the breaking. We keep on breaking, keep on breaking. Where do we break in the breaking? So in sort as well, are we handling that case of if next is null, return head or something like that, right? Because uh, yeah, if we don't, the base condition here would be if head is null or head dot next is null. You don't have to break further, just return head. Yeah, okay. So let's run. I'm thinking there might be a bunch of mistakes, but let's see. Okay, previous next is null. Where is this? Okay, not a statement. There is no previous. There is this previous, but define the previous. Everything is no such thing like this in Java. Okay, previous dot next is null. Okay, there's no such thing as node, it's called list node. Wrong answer. Okay, output is 134. Where did the 2 go? The good thing is you can sort the lists and you can print them, right? So let's do this. Let's just do this. Okay. These are the different calls that we get. To understand if you broke it properly. The first time around, okay. So we can't print it. Fine. So we can do something like print list head and write our own function. Okay, run code. What the heck? Okay, I am not doing head equals to head dot next. So we had this list 4213. Um, then we called it on 42, which called it on 4 and 2. And then we called it on 13, which called it on 1 and 3. So everything else was fine. Let's look at the merges then. Uh, what are the merges that we are doing? After these nulls and after these as well. Yeah, here. So I guess we want to do print list at 1, at 2, and we also want to call, hey, this is what we are merging. Okay. Let's see what happened. So we merged 2 and 4, which is good. And then we merge 1, 3, we go 1, 3. We merge 1 and 3, which is good. So when we merge my 1, 3 and 4, so the merge of 2 and 4 is not giving the right answer then. Let's see that as well. So the problem is in merge then. Let's see if there is a mistake here. Temp equals node 2. Node 2 will node under temp, so node next equals to temp. Um, that's okay. Uh, Let's see. So we are merging 2 and 4, and we are getting 2, 4. We are merging 1 and 3. Sorry, one. Yeah, we are merging 1 and 3. We're getting 1, 3. We are merging 1. Then why would we merge 1, 3, and 4? I don't understand. So if merge of 2 and 4 is returning 2, 4. Merge of 1 and 3 is returning 1, 3. So it should be 1, 3 and 2, 4, right? Maybe because we're not taking the result of that. Maybe, yes. So this sort list, right? So okay, this sort you have to take. We have to do merge sorted lists of sort list of head and sort list of mid. Yeah, not head and mid. Head and mid not necessarily remains the same. Yeah, so this is what we need to do. Now let's see. Yeah, return, and we return this as well. Perfect. So we can see 4213. First we did 4 2, broke it into 4 and 2, then we merge 2 and 4, we get 2 4, then this 1 3. 1 3 we break further into 1 and 3. Easy is the last, so we merge 1 3, we get 1 3. Then we merge 1 3 and 2 4, get 1 2 3 4. Okay. Now let us remove all the prints. Fine, submit. Okay, so time limit exceeded. That means um, all increasing, seems like. Let's take that example. Let's just do this. I don't know whether it's even or odd. Let's do first odd. Hmm. I'm also printing a bunch of stuff. Could be just the printing was taking a lot of time. Let's see. Yes, 1, 2, 3, 4, 5 works. 1, 2, 3, 4 works. Let's do 4, 3, 2, 1. I think we already did that, but okay. 5, 4, 3, 2, 1. And this works, and just 42, 4, 3, 2, 1. That works as well. Maybe and here we remove all the prints. So there are 3 of these. Remove here, remove here, remove here, and remove this. Run code. Submit. Alright, it works. Even though the time complexity is not that great. Okay, but for now, we'll stop here. Basically, using merge sort. There's already a problem called merge two sorted lists, and there's another problem called merge k sorted lists, wherein we can use a heap, but for two, this is the general pattern that we can use. And yeah, we keep depending on the list. So really is the time complexity and log n. Okay, that so for every let's consider whether it's really n log n or not. So what are we doing here? There are log n iterations when we're dividing the two, that is clear. In each of those iterations, um, merging is O of n overall, like at a single level if you're doing, and then find the middle also O of n. So yeah, so each of these log n iterations are needing us to go through n nodes twice, once to find mid and once to merge. So it is n log n actually. All right, and space we're not using any, so that should be fine. Okay, we can stop here.